Okay, number 25, they've given you an a of x function right here, and it's defined as an area accumulation problem, kind of similar to the one we did in notes at the end of 5.5, but they're asking you some different questions here, so I like this problem a lot. So they've defined a of x as being the definite integral from 0 to x of f of t dt, and this graph over here is that f graph. Now you'll notice here on the left it's f of t, here on the right it's f of x. Don't let that shake you guys. The name of the function is f. This is the graph of that function. And the first thing they want us to do right here in number 25 is to come up with the values of a of 2, a of 3, a prime of 2, and a prime of 3. So let's work on that. Okay, so to evaluate a of x, we're going to take a definite integral starting at 0 and ending at x. So we're going to make a region, I think I'm going to go green with this one here, that starts at 0 right there, and for starters, ends at 2. They want to know the net area between the curve and the x-axis starting at 0, ending at 2. Well, it looks like we have a 2 by 2 rectangle here. Some might even call that a square, and that's going to get us 4 for that area. Now for a of 3, we're not losing any of the area that we started. We're just going a little bit further, and we now have a trapezoid here that we need to add to the area of that rectangle. So let me just draw a little arrow right there, guys. The area of a trapezoid is always going to be 1/2 times its height, which in this case is horizontal right here. That'd be a height of 1, and then the sum of its bases. Looks like this base has a height of 2, and this base a height of 3. So 2 plus 3 means that the area of that trapezoid is going to be half of 5, or 2.5. Now we're going to add that 2.5 right here to the 4 that we had at 2 and get 6.5 or 6.5 for the total area of all of that green region right there. Okay, so that's a start. Now, you guys, if I'm guessing here, might have done okay on those two problems, and then maybe you had a problem on the second part, a prime of 2, but that's actually easier than what we were doing just a second ago. Let me show you what I mean. Let me get rid of some of this junk right here. So this is the function a of x. And what they want us to do is come up with the value of a prime of 2. So we need a prime of x in order to do that. Now, how are we going to do it? We're going to take the derivative with respect to x of both the left and the right side. The derivative of a of x is going to get us a prime of x. And on the right side, here's where the magic happens, derivative with respect to x of the definite integral from 0 to x. The derivative and the integral just wipe each other out, and we end up with f of x. So this statement right here, a prime of x equals f of x, tells me that a prime of 2 is just going to equal f of 2, and this is the graph of f. So at 2, the value of this function right here is 2. And a prime of 3 would be f of 3. And at 3, the value of this function here is 3 also. Now, it's a coincidence, guys. This won't always be the case that both of these values here matched those values perfectly. That's just a coincidence, and maybe a rather unfortunate one for the way they wrote this problem. I wouldn't want you guys thinking that that is always going to be the case. But anyway, that's where we're at with part A. Now in part B, they ask you to do something that I did not ask you guys to do in class. They want you to write specific formulas here for a of x, but valid only to a particular interval here. So this gets a little messy, and I wish I hadn't maybe done quite so much. Oh, maybe I can get rid of some of that stuff. Some of the green here. Okay, I'm just trying to get it back to what the original graph looked like before I messed it all up. So there. Let me get rid of that. That point didn't need to be there, neither did that. Okay, now we're making some progress, guys. All right, so what I want to do now is grab this whole graph here and bring it all the way down so we can see it here. Gotcha. And let's take a look at what's going on here. They want us to come up with formulas for a of x, first of all, on the interval here from 0 to 2. So to do that, what I might do, all right, let's run with it, guys. I'm going to ask you to do a little more than they did in the last problem. A of 0 is a region starting at 0, ending at 0. That's 0. A of 1 is taking us to here. That's an area of 2. And A of 2 took us all the way to here. That was 4. Now, if we look at those values here, guys, I'm going to ask you, what kind of pattern does it look like we're following here? Kind of looks like a linear pattern that's going up by 2 each time. So I think our formula here for a of x is going to be a linear function that I think is simply going to be 2 times x. Okay, and I think that should work pretty well. Now, if you notice, this isn't always the case, guys, but this part of the equation, should have done that in red, this part of the equation right here is just the line y equals 2. And if you anti-differentiated y equals 2, you'd get 2x. So that's kind of cool. Okay, on to the second part of it now. Let's do something from 2 to 4. So again, we already know that a of 2 is equal to 4, but I think we should probably find the value of a of 3, which we did already. That was 6.5. And then a of 4, which we haven't found yet. So let's see, if I went all the way to 4, let me think here, guys. I've got, again, all of this region here had an area of 4. I'm going to just treat this as one big trapezoid now. So area of the trapezoid would be 1/2 times a base of 2. And for the heights, I'm sorry, that was a height of 2. And for your bases, we've got a 2 here and a 4 on this side. So half of 2 wipes out 6 is the area of that trapezoid. And we now end up with 10. So that problem gets a little bit more complicated right there, guys, for how it is we might try to describe that relationship, because you'll notice we're not going up by a set amount each time. So this gets kind of interesting. Well, maybe we can kind of apply what we learned right here. The equation of this little linear function right here, that might help us out right here, guys. So it looks like that is going to be the line y equals, I think it's just y equals x. It goes from 2, 2 to 4, 4. Yeah, this is just the line y equals x. And if I were to anti-differentiate just that function right there, just on this interval here from 2 to 4, I think that would get me something like a 1/2 x squared. Now let's see what that would do for us. If I put a 2 in there, 1/2 of 2 squared is going to be 2. Not 4. Okay, that's a bummer. If I put a 3 in there, 1/2 of 3 squared is going to be 4.5, not 6.5. And 1/2 of 4 squared is going to be 8, not 10. But did you guys notice what I was off by each time? Each time I did that, I was missing a total of 2 here. So if I put a plus 2 there, that might get me what I needed. Let me check that again. 2 squared is 4. Half of that is 2. Plus 2 gets me 4. When I put a 3 in there, 3 squared is 9. Half of that is 4.5. Plus 2 is 6.5. Okay. And when we put in a 4, 4 squared is 16. Half of that is 8. Plus 2 is 10. So that one took some finagling here, but I think those are the formulas that they wanted for part B there in order for us to be able to express what a of x is on each one of those two intervals. Okay, so that one definitely took some work, but that's what they needed there on problem number 25.